Yo, mic check, mic check. Yeah, here you go. Oh, nah, he over here. Yeah, I heard he got that hot new thing. It's called Switch. Let's get it going.
The Switching Lemma. It originated in the works of Furst Saxe Sipser and of Yao. I'll show you the strongest form of the result, which was proven by Håstad. His proof included some simplifications suggested by Bapana and another Saxe. A fairly different looking version of Håstad's proof was given by Razbarov, and Beam wrote a popular exposition of that proof. In turn, Thapen made things even a bit slicker, and we'll follow this slickest route in the video. We begin by stating the switching lemma. Let's say that D is a DNF formula of width at most W. Just to remind you, a DNF is an OR of terms where each term is the AND of some literals. Its width is the maximum number of literals in a term. Let R sub epsilon denote the probability distribution on random restrictions with star probability epsilon. This means you map each variable xi to star, which means you leave it unfixed, with probability epsilon, and otherwise you fix it to 0 or 1 with equal probability, so 1 minus epsilon over 2 probability each. And you do this independently for each variable xi. Now, the switching lemma essentially says that if you let rho be such a random restriction, and you look at how D simplifies as a Boolean function when rho is applied, then it's overwhelmingly likely that D gets absolutely crushed. We measure this by looking at the decision tree depth of D restricted by rho. This means the minimum height of any decision tree computing the restricted function. What the switching lemma says is that for any parameter h of your choosing, if you look at the event that D restricted by rho needs decision tree height at least h, the probability of that is exponentially small in h. And the base of the exponent is some small constant like 10 times the width bound W on D times the star probability epsilon of rho. Crucially, there's absolutely no dependence on n, the number of variables in D, nor is there dependence on the number of terms. Let's think about this bound a little bit. We can start by selecting h to be 1. Now, to say that some function requires a decision tree of height at least 1 is just to say it's not a constant function. So the switching lemma tells you that D restricted by rho collapses to a constant function, either 0 or 1, except with probability at most 10 times W times epsilon. Now, that's actually not impressive unless epsilon is noticeably smaller than 1 over W. Remember that a term might have W variables, and epsilon is the probability that a variable is unfixed by the restriction. So epsilon being much smaller than 1 over W means that in a typical term, the expected number of unfixed variables is actually much smaller than 1. In other words, it's likely that most terms get all of their variables fixed. But there could be zillions of terms in D. We didn't say anything about that. So there can be plenty of terms that get 1 or 2 or several variables unfixed by rho. In any case, a good mental model is to think of W as relatively small, and to think of epsilon as, say, 1 over 20 times W. With this parameter setting, the right-hand side becomes 2 to the minus h. And so we get that the probability D restricted by rho is not constant, is at most a half. The probability it requires a decision tree of height 2 is at most a quarter. The probability it requires a decision tree of height 3 is at most 1/8, etc. I've collected here on the right the setup with D and W and epsilon, along with our goal, the statement of the switching lemma. Now let's think about what happens when we have some DNF D and some restriction rho, which fixes some variables to 0 or 1 and leaves the star variables unfixed. Underneath D here, I've written the assignments that rho gives to each variable. Let's look at the first term. x1 remains unfixed. x2 gets fixed to 1, which means the negation of x2 is 0. And this means that the whole first term here gets killed to 0. Each term is an AND, and as soon as one of its literals is made 0, the whole AND gets restricted to 0. x4 got fixed to 1, but that doesn't change anything. Now this first term got fixed to 0, but D is a big OR of terms. So for the restricted DNF, we can just delete this whole term, because a 0 doesn't affect an OR. Now let's look at the second term. The restriction rho fixes x2 to 1, so we can imagine deleting it from the term. x5 gets a star, so it's unfixed. x6 is fixed to 0, so negation of x6 is 1, so we can also delete it from the term. But we see that this term survives the random restriction rho. It gets shrunk down to just x5 though. On the other hand, in the third term, all 3 variables got set to star, so this whole term survives without shrinking. This is actually quite unlikely because row is supposed to set very few variables to star, but I wanted to show it as an example possibility. So in general, these are the things that can happen when the DNF D is restricted by row. Some terms get killed. It's possible that all terms get killed, in which case D restricts to the constant function 0. It's also possible that all literals in some terms get fixed to 1, in which case the whole DNF restricts to the constant function 1. Otherwise, some terms are killed, and the other terms possibly shrink. Remember, the switching lemma is concerned with the decision tree complexity of the restricted function. We want to show that it's very likely that it's computed by some shallow decision tree. Instead of trying to be smart about this, let's be dumb about it. Let's consider the dumbest way to build the decision tree for the restricted function. Given DNF D and restriction row, we'll define dumb decision tree of D and row as follows. First, if D restricted by row is already a constant 0 or 1, just make the decision tree a single leaf and you're done. Otherwise, find the leftmost term that's not killed. This is an example of being dumb. We're not going to try to cleverly find some small unkilled term, we'll just take the first one from the left. Next, have dumb decision tree query all the variables in that first unkilled term. This is also kind of dumb, because once you query the first variable, there's some setting for which the whole term gets killed, and there's no need to query the remaining variables in the term. But never mind, just obliviously query all the variables in this first unkilled term. Finally, having done that, you recurse. You've gotten new fixings for all the variables in that first unkilled term, you plug them into D, and you see if it's a constant now. If it's not, you look for the next unkilled term from the left. Here's a simple example. Row kills the first term, but the second term is unkilled. It has only x5 in it. So the first piece of dumb decision tree just queries x5. Now when x5 is 1, this second term becomes 1, and so all of D reduces to 1. On the other hand, for the setting of x5 equals 0, we move on to the third term. Here, negation of x5 is 1, so we can delete it, but x3 and x7 are star, so we have an unkilled term with 2 variables, x3 and x7. The dumb decision tree just queries both of them and then moves on. So notice that on the branch where x3 equals 0, we still go ahead and query x7, even though we already know this third term is killed. One more crucial thing to notice is this. Whenever the dumb decision tree queries a block of variables, there's always one particular outcome that satisfies all the literals remaining in the term. For this branch, the whole term is satisfied, which means that D becomes 1, which means that we can make a leaf. So whenever the dumb decision tree queries a block of variables, there's one branch that will lead to a leaf labeled 1. Okay, now remember the switching lemma says that if you look at the best decision tree for D restricted by row, it's very likely to have height less than h. In fact, what we're going to show is that it's very likely that even the dumb decision tree has height less than h. This is an even stronger statement, and it will be easier to prove because we don't have to reason about all decision trees for D restricted by row, just this one particular dumb one. Let's define a set of restrictions called bad. We'll say that a particular row is in the bad set if the dumb decision tree for D restricted by row has height at least h. So we can phrase our goal in a slightly different way. We want to show that the total probability mass of all rows in the set bad is at most 10w epsilon to the power of h. We're referring here to their probability distribution under the random restriction distribution with star probability epsilon. Here's a cartoon of a dumb decision tree whose height is at least the parameter h. That means it has at least one path of length at least h. So let's fixate on the leftmost path in the dumb decision tree of height at least h. I've shown it here in pink. For simplicity, I would like to assume that its height is exactly h. This should be fine since paths of length bigger than h are only more unlikely. Technically, there is a tiny bookkeeping step in the proof now where you have to truncate the path to height exactly h if it's longer than h. It's very boring to keep track of this technicality. It just adds like 3 boring sentences to the whole proof, so I'm going to ignore it. So we'll assume this path has height exactly h. We think of it as a new restriction, extending row, but fixing exactly h additional variables. And we're going to call this new restriction the devil of row. To summarize, every bad row has a unique associated restriction, devil of row, which extends it by fixing h additional bits. Let's focus in on this path down the dumb decision tree that generates devil of row. It comes in several pieces based on the way the dumb decision tree makes its queries. Remember, the decision tree first queries all the variables in the leftmost term that's unkilled by row. We'll call these variables v1. In this example, v1 is just the single variable x2. Devil of row fixes x2 in some way. In this example, it fixes it to 0. Based on this fixing, the dumb decision tree queries some other bunch of variables, v2. These are all the variables in the leftmost term of D that is unkilled by row together with the setting x2 equals 0. In this example, v2 is x4 and x5. The devil happens to fix both of these to 0 as well. Just to clarify this example, the restrictions row and devil of row might look like this. Moving on, based on these settings of v1 and v2, the dumb decision tree queries another block of variables, v3. In this example, x9 and x12. Here, the devil sets the first one to 1 and the second to 0, etc. With all of this set up, salvation is going to come in the form of another restriction based on row, what we'll call angel of row. Angel of row will also be a restriction that extends row by fixing exactly h additional variables. It's defined as follows. You look at the first block of variables queried by the dumb decision tree, v1. Remember that whenever the dumb decision tree queries some block of variables from an unkilled term, there's always one particular outcome that satisfies all the literals in the term, and hence satisfies the term, and hence gets to a leaf labeled 1. So angel of row will fix the variables in v1 in that one satisfying way. Now angel of row will also fix the variables in v2. Remember that v2 comes from the definition of devil of row. The devil restriction got us to some unkilled term where the unfixed variables were v2. And angel of row sets those v2 variables in exactly the way that would lead to the leaf labeled 1. Again, for each block of variables down the devil path, v3, v4, etc., the angel restriction fixes the variables in the unique satisfying way. Technicality alert, if we had to truncate the devil path to height h, then the angel restriction doesn't get all the way to a 1 leaf in the last block, but it's still defined to be the unique path that satisfies all the literals in that block. Anyway, I promised I wasn't going to talk about this boring technicality, so never mind. Things are getting a little complicated, so let me summarize where we are so far. For every bad restriction row, meaning one where the dumb decision tree has height at least h, we focus in on the leftmost path of height h. This is the devil path, and it fixes some variables v1 in some annoying way, then it fixes some variables v2 in some annoying way, etc. We let v be the set of all h variables along this devil path. Finally, angel of row is a restriction that extends row by fixing all the variables of v in the good way, the way that takes them to leaves labeled 1. To motivate all this, let me ask a question. Suppose we have a bad restriction row and its associated restriction angel of row. Which of these two restrictions is more likely under our distribution on random restrictions? The answer is that angel of row is much more likely. The reason is that angel of row is the same as row, except it has h fewer stars. And remember that stars are unlikely. They have probability epsilon. This is actually the key insight of the switching lemma. Sure, there's some chance of getting a bad restriction row, but it's much more likely that you'd get angel of row, which actually fixes d to the constant 1. Let's be more quantitative. For a particular restriction row, like the one shown, it's easy to write down its probability. You just have a factor of epsilon for each star, and a factor of 1 minus epsilon over 2 for each fixed bit. As for angel of row, its computation looks similar, except it will always have h factors that are 1 minus epsilon over 2 rather than epsilon. This means the ratio of the two probabilities is exactly epsilon over something close to a half, all to the power of h. So the ratio is basically 2 epsilon to the power of h. That's not quite right because the denominator, 1 minus epsilon over 2, is a teeny bit smaller than a half. But you could assume without loss of generality that epsilon is smaller than 0.1, because otherwise the 10W epsilon in the theorem statement is bigger than 1, making the theorem trivial. So that means 1 minus epsilon is close to 1, at least 0.9, and this factor that was roughly 2 is always at most 2.5, say. I'm being a little sloppy here. You can make this constant even a bit smaller if you care to. In summary, we see that for a bad row, its probability is exponentially smaller than its associated angel restriction. Let's do a brief calculation based on this. We just saw that for rho in the bad set, the probability of getting rho is at most 2.5 epsilon to the power of h times the probability of getting angel of rho. We'll now sum this over all rho in the bad set. Here comes the key, the linchpin of the entire proof. In a moment, we're going to show the following key fact. Any restriction rho is the angel of not too many different bad rhos. At most 4w to the power of h bad rhos, in fact. Remember, each bad rho has a unique associated angel, but the reverse is not necessarily true. Some restriction sigma might be the angel of multiple different bad rhos, but not too many different ones. This is what the key fact says. Let's take this key fact on faith for now and plug it into our calculation. We have the sum over all bad rho of the probability of rho's angel. Now, for a given restriction sigma, how many times can probability of sigma be occurring in this sum? Well, the key fact tells us at most 4w to the power of h times. So we can bound the whole sum by 4w to the power of h times the sum over all sigma of probability of sigma. But that summation is simply 1. Putting the other two factors together, 2.5 times 4 is 10, we get an upper bound of 10w epsilon all to the power of h for the total probability of all bad restrictions. That's exactly what we were shooting for. So to conclude, we've proven the switching lemma, except for proving this key fact. This is a good time for an intermission. This is the halfway point of the proof. Okay, on to the second half. On the right, I've depicted the ingredients of the proof that still remain. We have a bad restriction rho, meaning that the dumb decision tree for d restricted by rho has height h. We have the pink devil restriction, which extends rho by fixing h additional variables, querying the blocks of variables v1, v2, etc. And finally, we have the blue angel of rho, which also extends rho by fixing h variables, but always fixing the blocks v1, v2, etc. in the way that causes the associated term to be satisfied. Now, how will we prove the key fact? Let's suppose that sigma is a restriction that is the angel of some bad rho. We are going to describe a detective who, given sigma and a small clue, can determine what rho is. The clue will look like this scrap of paper with some numbers and commas and bits written on it. Don't worry just yet about how this clue will help the detective figure out rho given sigma. Instead, let's think about why this assertion allows us to prove the key fact. The clue for the detective will always have h positions, or columns of information. In the top row, each of the yellow numbers will be between 1 and w, where, remember, w is the width of the DNF D. This means there are w to the power of h possibilities for the yellow numbers in the top row of the clue. The bottom row of the clue consists of pink bits, each either 0 or 1. Again, there are h of these, so there are 2 to the power of h possibilities for this pink second row. Finally, you might not have noticed them at first, but the clue also contains some commas in white. These commas separate the yellow numbers into blocks. Each slot between two yellow numbers may or may not have a comma. There are h-1 possible slots, and therefore 2 to the power of h-1 possibilities for what the commas might look like. If we multiply these three quantities together, we get w to the h times 2 to the h times at most 2 to the h. This is 4 times w all to the power of h possibilities. What does this have to do with proving the key fact? Remember, we promised that whenever sigma is the angel of some bad rho, a detective that's given sigma can always pinpoint rho if they're given a suitable clue. But there are no more than 4w to the h possible clues, and therefore there are at most 4w to the power h possible rhos for each sigma. So to summarize, the only thing left to complete the whole proof is to explain what the clues mean and how the detective operates. Rather than directly telling you what the entire clue should be, let's put ourselves in the shoes of the detective who's trying to figure out rho given sigma. What kind of clue would we need in order to crack the case? It's important to remember that the detective does not get to see the structure of the decision tree, since the detective does not know rho. The only thing the detective gets to work with is some plain restriction, sigma, promised to be the angel of some bad restriction rho. In fact, the crucial thing for the detective to determine is the blocks of variables v1, v2, v3, etc. Sigma has particular bits, zeros and ones, for these h variables, whereas rho has stars for these variables. So once the detective knows these h variables, v1, v2, etc., they just have to put stars into sigma for those variables, and the result is rho. So let's imagine the detective at the beginning of the investigation. They know D, the DNF, and they know sigma. What can they deduce about rho? Let's ourselves imagine rho, even though the detective doesn't know it yet. And let's recall how the dumb decision tree for D restricted by rho was created. You plug rho into D, and then look at the terms from left to right. Some terms get killed by the restriction rho, and then there will be some first term that's unkilled by rho. We're mentioning rho is bad, so D is not simplified all the way to a constant. Now, the detective doesn't know rho, but they do know sigma, and also D. So let's suppose the detective imagines plugging sigma into D. Again, looking at the terms from left to right, it holds that every term that is killed by rho is also killed by sigma. This is because sigma only fixes more variables than rho does. On the other hand, let's consider the first term that rho leaves unkilled. In this term, rho fixes some literals to true, x1 bar is fixed to true in our example, but rho leaves the rest of the variables in this term unfixed. These unfixed variables are precisely the variable set v1, namely x2 and x8 in our example. At the same time, by definition of being the angel of rho, sigma fixes these variables x2 and x8 in exactly the way that causes this term to be satisfied. So this first term unkilled by rho is satisfied by sigma, and in fact it's the first term from the left that's satisfied by sigma. This is great news for the detective. It means if they take sigma and plug it into D, the leftmost term that is satisfied must contain v1. Now, before we get too excited, it's crucial to note that the detective hasn't figured out v1 yet. They've only figured out that v1 is some subset of this term with x1, x2, and x8. Sigma will be fixing all of these variables to bits, whereas rho left some of them, namely x2 and x8, as stars. But of course, this is where the clue will come in. The clue will teach the detective what v1 is by specifying the positions of the v1 variables within this leftmost satisfied term. More precisely, since v1 is x2 and x8, and these are positions 2 and 3 within the term, the clue will contain the numbers 2 and 3, followed by a comma to signify that that's all of them. A critical point for the proof is that the clue doesn't just state the variable names x2 and x8, because there are n possibilities for each variable, which is way too many. The clue exploits the fact the detective has pinpointed a term containing the variables of v1, and this term has width at most w. So each variable in v1 can now be clued using a number between 1 and w rather than between 1 and n. At this point, the detective has made great progress because they know exactly v1. Of course, they now want to move on to learn v2, but they need a bit more information for that. Referring to the diagram on the right, you'll recall that the identity of the variable set v2 depends on how the devil restriction sets the variables of v1. But it's not very costly to also put this information in the clue. The clue can have those two bits, in our example 2 zeros, written in the corresponding positions. Now the detective has all the information they need about v1, and they can begin the process of learning v2. You might get the sense that we're pretty much done, that the detective can learn v2, v3, etc. by repetitions of this process. And that is more or less true, but it's worth it to still go through things a bit carefully. Having figured out how the devil fixes the bits of v1, what the detective does now is change sigma to have the devil's pink bits for these variables. We've denoted this by changing sigma to a pink sigma prime. This sigma prime is kind of a hybrid between the original angel restriction sigma and the devil restriction. The detective is going to slowly morph the angel restriction into the devil restriction, all the while learning v1, then v2, then v3, etc. Once the detective has completely morphed sigma into the devil restriction, it will have learned h variables in the blocks v, and then the detective just has to change all of these variables to stars, and it will have recovered rho. Let's recap where we are. Rho is a bad restriction, and sigma is the angel of rho. Given sigma and the clue so far, we imagine the detective has figured out v1 and the devil's bits for v1, and has formed sigma prime by substituting the devil's bits for v1 into sigma. Now it's time for the detective to figure out v2. The process is similar to figuring out v1. Let's look again at D, the DNF, sigma prime, the restriction the detective knows, and the original bad restriction rho. Remember that when rho is plugged into D, it kills some terms on the left, then leaves some term unkilled. The unset variables in that term are v1. Now the devil restriction fixes all these unset variables from v1, and it does so in a way different from the angel. That means the devil bits kill this term to 0. Just as before, sigma prime only sets more variables than rho, so it kills all the terms rho kills. Also, sigma prime has the devil's bits for v1, so it also kills this term that gave us v1. A good question to ask ourselves now is, what is the set v2 the detective is trying to find? Where does it come from? Well, it's defined by the process for creating the dumb decision tree. We continue going through the terms of D, seeing if they are killed by the combination of rho and the devil's bits for v1. Any term that is killed will also be killed by sigma prime, because sigma prime has rho's fixed bits and the devil's bits for v1. When we reach the first unkilled term, this determines the set v2. You can check that in our example. This is the very next term, the third term. Here, the combination of rho and the devil's bits for v1 reduces this term to just x4. That's why the set v2 just contains x4. And similar to before, this term will be satisfied by sigma prime because sigma prime still has the angel's bits for v2. So we have a similar situation. The leftmost term of D that is satisfied by sigma prime contains the set v2. Since the detective knows D and sigma prime, it can find this term. In our example, it's the third one with x2, x4, x5, and x6. Here, the detective already happens to know that x2 is in the set v1, but of the remaining variables x4, x5, and x6, it doesn't know which are in v2. Again, the clue now comes into play. The clue specifies the variables in v2 by specifying their positions within the term and then writing a comma. Here, v2 is just a single variable appearing at position 2 in the term, so the clue just has a single yellow 2 for that position, followed by a comma. Once again, in order to proceed to v3, the detective needs to know how the devil sets the v2 variables. In this case, I put needs in quotes because when there's only a single variable, the detective can infer that the devil sets it the opposite way from the angel. In our example, the devil sets it to 0 rather than 1. But let's not over-optimize. We'll stick the pink devil bit for v2 into the clue anyway, to keep the story simple. So now the detective can update sigma prime, changing the x4 bit from the angel's 1 to the devil's 0. And now the detective has made great progress. They successfully learned the variable sets v1 and v2. Moreover, they've updated sigma prime to contain the devil's bits for v1 and v2. And this means if they now plug sigma prime into D, the leftmost satisfied term will be the one that contains v3. And again, the clue will let the detective know exactly what the set v3 is, as well as how the devil fixes the v3 variables. And so on, until the detective finally figures out all of the set v. And just to remind you, the detective can now finish the job of recovering the bad rho simply by putting stars into sigma in the v positions. The proof is now complete, but let me recap how it went. We just showed that whenever sigma is the angel of some bad restriction rho, there is a suitable clue that a detective can use to recover rho from sigma. Our clues had a very simple format, and we counted that there are always at most 4w to the power of h possible clues. From this, we inferred the key fact, that any restriction sigma can be the angel of at most 4w to the h different bad restrictions rho. In turn, this lets us do a probability calculation. We saw that a bad rho is always much less probable than its angel, by a factor of like 2.5 epsilon to the h. And so the total probability mass of all the bad restrictions rho is at most 10w epsilon to the power of h times the total probability mass of all potential angels sigma, which is just 1. And that finally gave us the switching lemma, which, to repeat, says that for a DNF D of width at most w, In a random restriction row with star probability epsilon, it's exponentially unlikely that D restricted by rho will need a deep decision tree. In particular, the chance it needs a decision tree of height at least h is at most 10 W epsilon to the power of h.
Friday night and the lights are low. You're looking out for a place to go, where they play the right music, where they get in the swing.